The next section, section 13.4, is called randomized block design. This is also an analysis of variance test, ANOVA test, except that here we have an additional factor. And this factor is called a block factor because the variation that this factor contributes to the response variable is not something we are interested in. So we need to figure out what amount of variation is contributed by the block design and then get rid of it or block it from entering our analysis. And that's the reason why this is called block design. Now, some examples. Suppose we have 3 different assembly methods and we are trying to figure out whether there are any differences in terms of productivity of these different assembly methods. But the productivity may also be variable due to the skill levels of workers. So different workers with different experiences may contribute to the productivity as well. But we are interested only in the productivity contribution by the assembly method, and we are not interested in the differences contributed by the differences in the worker experience and skill level. And therefore, in this example, the productivity of assembly methods, the factor of interest is the different assembly methods. The factor that is there but we are not interested in is the workers, differences among workers. So differences among workers is the block factor. One more example, we have different feed regimens that we feed to our milk cows. We are interested in the differences in the yield of milk that is attributable to the differences in the feed regimen. But it is possible that there are some inherent differences in the cows themselves that contribute to the yield of milk. So here the factor of interest is feed regimen, but the factor that we are not interested in is the differences among cows. So the cows becomes our block factor. One more example, cost of items among retail stores. And we want to see whether there are differences in different retail stores, some discount store or Walmart or Target and so on. Are the prices different from in different stores? So here our factor of interest is stores. Is there a difference due to different stores? But then the prices among the items themselves differ. But we are not interested in the differences in prices due to the differences in the items. So the retail stores is your factor of interest and the items themselves are block factor. Okay. Now, the hypothesis that we want to test is exactly like before, whether the factor of interest, the means are same or not. We are not interested in the block factor. We are only interested in the factor of interest. Now, so we have k populations, that is k factor levels, and whether all the means are same or not. To test this hypothesis, we have to make some assumptions, and these assumptions are exactly like before. For each of the population, that is each of the factor level, the response variable follows normal distribution. The variances of the response variables are all equal among the different populations or treatment levels. The observations are independent, or samples are independent. Take samples, and here we have treatments 1 through k, and in the block level we have exactly the same number of blocks for each treatment. So if it is cows, so it will be like cow 1, cow 2 and so on. If it is items in the retail stores, it will be item 1, item 2 and so on. Or in the case of production, it will be worker 1, worker 2 and so on. And the treatment levels are k. And here we have b levels of block, lowercase b. So each treatment we will have observations going from x sub 1 1, x sub 2 1 and so on through x sub b1. The first subscript is row, the second subscript is column, and then the second sample that also has b observations, and so on until the kth treatment. So each treatment level has exactly b observations, b being the number of levels of the block factor, and for each row, that is each level of block, we have k observations, one for each treatment. So now we find the mean of the block to be x bar sub 1, that is for the first row, and then the column is dot. So the dot refers to the fact that we have averaged out the entire k columns for that row. So x bar sub 2 dot is the sample mean of the second row, and x bar sub b dot for bth row. Similarly, we can find sample mean for each column, that will be x bar dot 1. So the first subscript being rows, and we have averaged all the rows, and this is for the first column, x bar dot 2 and x bar dot k. And then the total number of observations then is k times b, number of columns times number of rows. That is our total number of observations in the sample. At this point, we'll run the block design ANOVA in data analysis in Excel, and that will produce the ANOVA table for us. The ANOVA table will have the sums of squares. We have SST, that is the total sum of squares, is divided into 3 subsections of this sum of squares. Sum of squares treatment with k number of levels of treatment. SSBL stands for sum of squares due to block, and then SSE is sum of squares due to error. Here are the formulas for SST, SSTR, and the block SSBL, and the sum of squares error is then computed by subtracting the sum of SSTR and SSBL from SST. And the degrees of freedoms are noted here. For treatment, it is k minus 1. For block, it is b minus 1. And for error, is k minus 1 times b minus 1. Now we can arrange all of this in an ANOVA table. So here we have treatment, block, error, and total. So we are not interested in the block, so we don't have to compute the mean square for block. So we compute mean square for treatment and the mean square for error, and MSTR divided by MSE gives us the F statistic. Then we use the F dist dot RT to find the p-value. So test statistic F is MSTR over MSE, and the p-value is found using the F dot dist dot RT function. Now, if the p-value is less than or equal to alpha, we reject the null hypothesis. Otherwise, we cannot reject the null hypothesis. So we look at an example in the next video.